I am Sunanta from SNS College of Technology, Department of Mathematics. As the continuation of the lecture series in the topic Eigenvalue problems, we are going to see a topic called Leslie model, a case study and interpretation in this lecture video. So first let us see about Leslie model. So this Leslie model was developed by Patrick Leslie in 1940 for age-textured population growths. Here we can also find the population decrease also. So this is used in ecology, so animal population and demography, human populations. So this method can be used to find the population growth. Next is, here we assume discrete age classes and constant vital rates. So here for this problem, for this model, first we will frame a matrix. So first is square matrix with row or column for age classes. So we will frame a square matrix with rows and columns for age classes as the first step. Next is first row. So first row is birth rates. Second one is subdiagonal, so which is the survival rates. Next, other elements are fixed as 0. Next is constructing the Leslie matrix. So this also requires birth rates and survival rates for each age class. For example, 2 age class if we take juveniles and adults. So birth rate as 0 and adults as 2. Next is survival rates of juveniles as 0.5. So we can fix the matrix as 0 to 0.5 and 0. So next is we are framing eigenvalue and eigenvector using this. So here the dominant eigenvalue is fixed as lambda. So the population growth rate. So if the lambda is greater than 1, then it is growth, and if it is less than 1, then it is a decrease or decline. If the lambda is equal to 1, then the rate is stable. For example, next is eigenvalue. So this is stable age description. Here next we are going to see interpretation of the model. So this lambda predicts the long-term trends and the stable age distribution guides the management strategies. Next is case study of turtle population is what we are going to see in this video. So which is here the age classes as hatchlings, juveniles and adults. The Leslie matrix forms the data as lambda is equal to 1.05, so which is the 5% growth. Next is stable distribution, so mostly juveniles. Title limitation of the Leslie model. So this assumes constant vital rates and this ignores migration, density dependence, environmental factors. So this may not apply to complex populations. If for example weather icons, migration and all cannot be calculated using this. Now we are going to see an example problem based on this. So here we are going to take the two age classes, with one is juveniles and another one is adults. So first let us construct the Leslie matrix as seen before. So here 0 to 0.5 and 1 is the Leslie matrix. So next we are going to frame the characteristic equation using a minus lambda I equal to 0. Therefore we will get minus lambda to 0.5 and minus lambda as the characteristic one. So next we are going to frame the characteristic equation by taking determinant of a minus lambda I, which in turns we will get lambda square minus 0.5 into 2 equal to 0 as our value. So which in turns gives the eigenvalues as 1, minus 1. So next is eigenvector, which in terms we will get a minus lambda I. So in that we are going to apply lambda value as 1. We will get 1 to 0.5 and 1 for lambda equal to minus 1. When we take lambda is equal to plus 1, we will get it as minus 1, 2, 0.5 and minus 1. So on solving both, we will get the eigenvector as 1 and 0.5. Next, to find the stable distribution, we can apply and solve we can, when we apply this in the population rate, we will get 2 by 3 as juveniles and 1 by 3 as adults. Thank you.